All right, guys, so now we've spent a little bit of time in class, and I've made a video about combining vectors, which was taking two or more vectors and combining them into one vector. So we call that vector addition or vector combination. We got one resultant out of two or more starting vectors. So now I want to talk about the opposite of that, the opposite of combining vectors, which is taking one vector and splitting it up into component pieces. This is something that has two different names. Sometimes it's called vector resolution, and sometimes it's called vector decomposition. You'll hear either of these phrases. I'll use both of these phrases, vector resolution and vector decomposition. Decomposition, that word makes a little bit more sense to me. You're decomposing or breaking the vector up into pieces. But sometimes you'll hear me say resolve the vector or decompose the vector, break the vector up into pieces. So to explain what I mean by this, let's imagine I had a vector. Let's say I had some vector here, v, and v could have any value. Let's just, for this example, let's make v have a value of 8. I don't know, maybe it's a displacement vector, maybe it's 8 kilometers, or it could be a velocity vector and it's 8 meters per second, whatever the 8 is. It doesn't matter for us right now. But I might ask you, for instance, is v pointed up or is it pointed to the right? Is it going up or is it going to the right? And you would say to me that it's going both up and it's going to the right. So the question is, how much of the 8 is going up, vertically upwards, and how much of the 8 is going to the right? Some vectors it could be more up than to the right, or it could be more to the right than up. So you might want to come up with a value. In other words, you might want to know, if I take a look at this, how much of this vector is going to the right? That would be this. And then how much of the vector is up? That would be this. So you can see this vector appears to be going a little bit more to the right than it is up. And these, what we call these two arrows that I've just drawn, these two blue vectors, are the components of the vector v. The component that's going horizontal, we call the horizontal component, or sometimes called the x component, the horizontal or x component. X because you think of horizontal as being the x-axis. And then the up and down component, the component of this vector v that's going up, is called the vertical or y component. So the vector v has two pieces. It has a horizontal piece and it's got a vertical piece. And you might want to calculate exactly how much the vector is horizontal and exactly how much of the vector is vertical. In other words, you might want to know, what are the lengths of these two vector arrows? How big are these vectors? It should be obvious to you, this is a right angle here, right? This here is a right angle. So we've got a right triangle where the vector v is the hypotenuse. Now, where before, in previous lessons, we've been going from two vectors, which were the legs of the right triangle, to finding the hypotenuse, which we called the resultant. And like I said, now we're going backwards. We have the resultant, in a sense. We've got the hypotenuse of the right triangle, and now we've got to work backwards to find the legs of the right triangle. So this is, hopefully you can appreciate how this is the opposite of what we were doing before. So now to split this vector up, to break it down into a horizontal component and into a vertical component, there's one piece of information I need to know. I need to know one of these angles. I need to know this angle here or that angle there. I need to know one of those angles, and if it's not obvious to you yet why, you'll see soon. So let's say that this angle here is 30 degrees. I'm just going to give that to you, 30 degrees. That would mean, of course, the other angle in the upper right-hand corner there would be 60 degrees, right? Because those two angles have to add up to 90 degrees. So we've got this angle here, 30 degrees. And I want to use that angle to determine what is the size of the horizontal component and what's the size of the vertical component. Before we do that, I want to, some of you might already realize how we're going to do this, but I want to review a little bit of geometry that that you've learned. Certainly, this is a little bit of trigonometry, that if I have a right triangle, there's my right triangle, that if I have some angle, let's say I've got an angle there, okay, we could call that angle anything, let's call that angle theta. There's a relationship between the legs of the triangle and the hypotenuse. So here's the hypotenuse. I'm going to call the hypotenuse H. And then we have a leg right here. This leg right here is opposite from theta. We call that the opposite side, O. And then this leg right here, that leg is adjacent to or next to theta. We call that A. So I've got a right triangle with some angle theta. And we've got three sides. We've got the hypotenuse. Hypotenuse is opposite the right angle. Then we've got the opposite side, which is opposite from theta. And then the adjacent side, which is adjacent to or next to theta. And hopefully you remember from geometry, SOHCAHTOA. SOHCAHTOA tells us the relationship between these three functions, sine, cosine, and tangent, and these three sides. So to remember what this is, so sine of theta equals the opposite, O, over the hypotenuse, H. Cosine theta equals adjacent, A, over hypotenuse, H. And TOA, tangent theta equals opposite O over adjacent A. Going through this quickly, you've learned this at least once before, probably several times before. SOHCAHTOA, the relationship between the sides of a right triangle and the angles of the right triangle, sine, cosine, and tangent. So I'm going to use this relationship. Make sure that you understand it moving forward. If you don't understand this, take a minute now, pause the video, and try to digest what's going on in this picture. If this isn't so fresh in your head, if you're still confused, come see me for extra help. But we're going to use the trig function sine, cosine, and tangent to resolve or decompose our vector here. So let's go ahead. Let's find the x component. The x component of the vector is going to be this adjacent side, this side that is adjacent to or next to the 30-degree angle. So I know the hypotenuse, that's the vector 8, and I know the angle theta is 30, and I'm looking for the adjacent. So I need to remember which trig function is going to help me here. If it's adjacent and hypotenuse, it's cosine is adjacent over hypotenuse. So I can say that the cosine of theta, 30 degrees, equals the horizontal or x component. I'll call that v sub x. That's the x component of v over 8, which is the vector, the size of the starting vector. Again, this horizontal component I've called v sub x. And so now I just need to solve for v sub x, and hopefully you can see here v sub x. I'm just going to multiply both sides by 8, is 8 cosine 30. Do out the cosine of 30 degrees is like 0.866. So you go ahead and multiply this through, and you find that v sub x equals about 6.9. Again, I have no units. We haven't decided what kind of vector this is. I haven't said it's a displacement vector or a velocity vector or acceleration vector. It could be any kind of vector, but the relationship here, because of the 30-degree angle, if the vector has a value of 8, the horizontal or x component has a value of 6.9. So that's the x component. Now let's try to find the vertical or y component. So I'm looking now for the y component. My angle is 30 degrees. I've got the hypotenuse, so I have to remember which function is going to allow me to find the y component. And I hopefully can see that I'm going to need the sine function. Sine, so, in SOHCAHTOA, is opposite and hypotenuse. So I say the sine of 30 equals the opposite, which is my y component, v sub y, over the hypotenuse, which is 8. Multiply both sides by 8, and I get v sub y equals 8 sine 30 degrees. The sine of 30 degrees is 0.5, so this has a value of 4. I'd be sure that double check my math. I may have, who knows, maybe I made another mistake, hopefully not. But make sure that you can get these answers. If you're not getting these answers, do check again to make sure that your calculator is in degree mode and not radian mode. As I mentioned before, when you're using these angles in your sine and cosine functions, you absolutely need to be in degree mode, because this angle 30 degrees is given in degrees. I didn't give it to you in radians, so make sure that you're in degree mode. You should get the right answers here. And so now we have succeeded in taking this vector that was at a 30-degree angle and splitting it up into horizontal and vertical components or pieces. Again, this should be obvious to you, hopefully it is, that this is the opposite of what we were doing before. This is the opposite of taking 2 and making 1. Now we've got 1, we're making 2. It might not be immediately obvious to you why this is going to be important. You might ask yourself, why the hell would I want to take a vector and split it into 2 vectors? It seems maybe like it's counterproductive or like taking a step back, but we're going to see that vector resolution is going to be very handy to us in some of the physics problems that we do in 2 dimensions. It's frequently really helpful or necessary to be able to take a vector and split it up into a vertical piece and a horizontal piece. So it is necessary that you have some comfort with this. Hopefully you followed that. Hopefully it's made sense to you. Review the SOHCAHTOA, that piece of trigonometry if necessary, because we are going to practice this in class, next class, and we're going to be using it for the next several months. So it's going to be with us for a while. So hopefully that makes sense. And we'll discuss it and practice it again next class.